Okay, problem number 6. A culture of 5,000 bacteria triples every 20 minutes. So let's think about it. We're starting with 5,000. After 20 minutes, it's going to triple. So think of that as multiplying by 3, and that's after 20 minutes. After 20 minutes. And we want to represent the population here with an equation. So think about what happens. After the first 20 minutes, I get this expression right here. But then after 40 minutes, so the second batch of 20 minutes, I need to be here. I need to triple again, so I need to multiply by 3 again. And then after 60 minutes, it's going to be the same idea, except 3 cubed. And then after 80 minutes, 5,000 times 3 to the 4th, etc., etc., etc. But notice that this expression is not really in terms of time, t, and that's what we want. So think about what we need to do to that exponent to make it in terms of t. Well, the first one, if we made that exponent in terms of t, it'd be 20, but we know that it needs to be 1, so let's put it over 20. Here, it would be 40, but it needs to be 2, so it's going to be 40 over 20. Here, it would be 60 over 20. Here, it would be 80 over 20. So notice what's happening. We're getting P of t equals 5,000 times 3 to the power of time divided by 20. Think about why that makes sense, because then every 20 minutes we're going to get an integer as our exponent, and that's what we want. After the first 20 minutes we'll get 1, second 20 minutes we'll get 2, third 20 minutes we'll get 3, etc., etc., etc. And if you think about it, this is a lot like that modified half-life problem that we came up with the other day, where you take time and divide it by the half-life, and that is the exponent on the 1/2, because that's the time it takes to halve in size. Well, this is the time it takes to triple in size, so the format of the equation is exactly the same. That's kind of cool.